Hey folks, welcome back. In this video we're going to go over question 3 from the 2021 SQA Advanced Higher Physics exam paper, so let's get going. Question 3 says the apparatus shown in figure 3a is used to investigate conservation of angular momentum. So we have a rotating disc and a falling mass over a smart pulley. And it says a sensor in the smart pulley is used to determine the angular velocity and angular acceleration of the rotating disc. Part A says during one experiment the torque applied to the rotating disc is 6.30 times 10 to the minus 3 Newton meters. This torque produces an angular acceleration of 0.618 radians per second squared. Show that the moment of inertia of the rotating disc is 1.02 times 10 to the minus 2 kilogram meter squared, and there's 2 marks available here. Well, writing down what we know from the question, we're trying to find the moment of inertia I. We know the torque tau is 6.30 times 10 to the minus 3 Newton meters, and we know the angular acceleration alpha is 0.618 radians per second squared. So writing down our equation relating moment of inertia, torque, and angular acceleration, we have tau equals I alpha. Rearranging for the moment of inertia I, we can divide both sides by alpha to get I equals tau over alpha. Substituting in the numbers gives 6.30 times 10 to the minus 3 divided by 0.618, and putting that into your calculator should give you an answer of 1.02 times 10 to the minus 2 kilogram meter squared. B part 1 says state the principle of conservation of angular momentum, and there's 1 mark available for this. Well, to answer this we can say it's the total angular momentum before an interaction is equal to the total angular momentum after an interaction in the absence of external torque. And the phrases that are underlined here are phrases that you need to mention to get the mark. B part 2 says in another experiment the rotating disc has a constant angular velocity of 7.75 radians per second. A small cube is dropped onto the rotating disc close to the axis of rotation. The cube remains at a constant distance from the axis of rotation. The angular velocity of the rotating disc decreases to 5.74 radians per second. Determine the moment of inertia of the cube at this position, and there's 3 marks available here. Well, to answer this we can let object 1 be the small cube and let object 2 be the rotating disc. And then using the principle of conservation of angular momentum we can say that total angular momentum before the interaction is equal to the total angular momentum after the interaction. And in symbol form, because there's 2 objects, we can say that's I1 omega naught 1 plus I2 omega naught 2 is equal to I1 omega 1 plus I2 omega 2, where remember the 1s here are representing the small cube and the 2s are representing the rotating disc. Well, we can simplify this straight away by looking at the left-hand term here, which we can say is equal to 0 since the small cube is initially stationary. And on the right-hand side, we can say that omega 1 is equal to omega 2 is equal to omega since both objects combine. So since the cube and the disc are combined after the interaction, then they must be rotating with the same final angular velocity. Now we can therefore simplify this line to I2 omega naught 2 equals I1 plus I2 times omega, where all we've done is factorise this right-hand side since we have I1 times omega plus I2 times omega, and therefore that's the same as writing I1 plus I2 times omega if you factorise it. So from this line of working, remember it's this I1 that we want to find, i.e. the moment of inertia of the cube. And then substituting in the numbers, we have 1.02 times 10 to the minus 2 for the moment of inertia of the disc, times 7.75, which is the initial angular velocity of the disc, is equal to I1, the moment of inertia of the cube, plus 1.0 times 10 to the minus 2, again for the moment of inertia of the disc, times 5.74, which we're told is the final angular velocity of the rotating disc, and therefore it must be the final angular velocity of the whole system, i.e. the disc plus the cube. Now expanding this right hand side and then swapping the sides, it becomes 5.74 I1 plus 1.02 times 10 to the minus 2 times 5.74 is equal to 1.02 times 10 to the minus 2 times 7.75. And then to simplify this, you could do the right hand side in your calculator first, and then subtract this part here, and then divide both sides by 5.74 to get I1 on its own. And if you do that in your calculator, you should get an answer of I1 equals 3.57 times 10 to the minus 3 kilogram meter squared. Lastly, B part 3 says the small cube is removed and the disc is again set to rotate at a constant angular velocity of 7.75 radians per second. A small cube of greater mass is now dropped onto the rotating disc. This cube remains at the same distance from the axis of rotation as the cube in B part 2. State whether the resulting angular velocity of the rotating disc is more than, equal to or less than 5.74 radians per second. You must justify your answer, and there's 2 marks available here. Well, we can say that the resulting angular velocity of the rotating disc will be less than 5.74 radians per second, since the moment of inertia of the system will be greater. So because the moment of inertia of the cube can be assumed to be the moment of inertia of a point mass, that would just be I equals mr squared. So moment of inertia and mass are directly proportional. So the greater the mass, the greater the moment of inertia of the cube. And if we look back at our working here, which could also be used to find the final angular velocity of the system, omega, then notice how it depends on the moment of inertia of the system, I1 plus I2. So to get omega on its own, you would divide both sides here by I1 plus I2, i.e. the total moment of inertia of the cube plus the disc. So if the disk's moment of inertia stays the same and the cube's moment of inertia is greater, then this total moment of inertia of the system will be greater, and therefore you're dividing by a greater number, which will give you a smaller final angular velocity omega. So that's why the resulting angular velocity omega will be less than 5.74 radians per second. That's all for this video, folks. Thanks for watching. If you made it to the end, I really appreciate it. Make sure to give the video a like, subscribe to the channel, and I'll see you in the next one. Take care.